Hi everybody. I hope that you're enjoying the RISC-V workshop because I am. It's really nice to be here. And today's talk is going to be about enhanced LLVM support for RISC-V that we have in our solution. So if you look at the agenda, firstly I'm going to introduce who we are, what we do, our product, and so on, and why we think that the SDK should be aware of every single instruction that you have inside of our solution. After that, I will dive into the LLVM internals and how we do stuff in more details. And because LLVM is not just a compiler, LLVM is a bunch of tools. So we also, we're also doing DB for debugging. We have some profiling options as well. So these tools are part of the SDK as well, and those tools should be aware of custom extensions as well. So let's start with the company overview. So who we are. So well, we are a pure-play IP provider of RISC-V, compliant IP provider with design tools. So, you can get an IP package as any other vendor from RISC-V, but we also have additional value in the design tools, and I will talk about it later on. The first RISC-V IP that we introduced was in 2015, which is 4 years ago. The company was founded in Brno, in Czech Republic. Brno is a very nice city. It's small enough and big enough at the same time. It's a university city as well. One of the really good universities are there. But we have a sales representative worldwide. So for instance, in Taiwan as well, in Korea, Japan, and all over the world. We're a founding member of RISC-V Foundation, so we joined quite early. And as you guessed from the previous presentation, we're a member of several working groups, such as compliance or trace and others. Well, LLVM is open source project, so whenever we find a bug or some improvements, we try to open source it as well. So we're active in the open source community as well, not only the LLVM, but mainly LLVM. So if you focus on the RISC-V IP and what we offer, well, we have a family of RISC-V compliant IP called Berkelium as a tribute to guys from Berkeley who invented the core in the first place, RISC-V core, ISA, to be more precise. So right now we have 4 implementations. The implementations differ, on the microarchitecture complexity. So we have really simple, pipeline-less design. It's called BK1. We have a 3-stage BK3 and a 5-stage BK5, and finally BK7 is 7-stage. The first 2 are 32-bit only. BK5, there is an option having 32-bit or 64-bit. BK7 is 64-bit Linux-capable core, so it's the most complex one. Well, we have just 4 microarchitecture to choose from, but on the other hand, we have several configuration options, either on the instruction set level or on the microarchitecture level. So in fact, we have like dozens and dozens of different IP in the end of the day, depending on the configuration. And because we believe in differentiation and the domain-specific optimizations, we allow you to do also, you can add your own instructions if you need to, or you can add your secret sauce in terms of microarchitecture things. So we don't stop you, in doing the domain-specific optimizations, but more on that later on. So speaking of configurations, so if we look at the options that we have right now, so we have implemented the standard ISA modules such as I, E, the M for multiplication, division, the C for compact instructions, F or D for floating point operations. We also have already, B, like bit manipulation instruction set extension already. P as well, we're working on V. So those modules are marked as work in progress because they are not ratified yet, but hopefully will be soon. And thanks to the technology that we have, we use, we rely on, we can quite easily add whatever ISA extension is ratified sooner or later. It's, the configuration, right now you can see the configurations that are available on the ISA level, but we have also, some options on the microarchitecture level, such as caches. So you can configure, how big the cache is, lines, and these kind of things. You can configure on-chip debugging, so you can, set select the different features that you might need or might not need depending on your final design. So, if you combine the ISA options together with the microarchitecture options, the range of IP portfolio is quite wide. And for some customers, it's okay to stop there. And okay, I just need RV32 IMC, and this is all I need. And we are happy with that, and we have customers that do that. But some of them say, well, it's not enough. We need more power, or we need more performance and less power, or we really need this special custom interface because we need to talk to some other hardware block that use the custom interface. So for them, we have a solution as well, because IP comes with a design tools that allows them to do these changes, these additions. And for them, it's really key thing, because they can add key differentiation to their product. They can add their secret sauce to the microarchitecture, for instance. And we allow them to do so. But at the same time, if you do that in a traditional way, in the standard customization way, you have to do manually a lot of tasks. You have to create a model and simulation. You have to change compiler. You have to change low-level tools like assembler. Not only that, you can also should change a debugger or disassembler as well. So then, when you're debugging system, then the system is aware of, or the SDK is aware of what you've done. And if you do this in the manual way or semi-automation way, then it's quite challenging, because you have to have experts in certain domains, and then you need to check that those experts did the same job, and that they added the same functionality properly. So you need to verify a lot, to test a lot, that those changes match each other, which is possible. And some companies doing that, and it's okay, but it's time-consuming and challenging and expensive in the end of the day, because you have to have experts in several teams. So we think that it's really useful to have as much automation as possible there. And this is what we do. This is the secret sauce that we have, the design tools that allow you to do this in the most automatic way possible. So if you do it in our way, which means that you describe the extension, so either the instruction set extension or microarchitecture secret sauce, you can describe that in one place only. You should describe that in an architecture description language that we have. And we take this description and we generate the compiler, the debugger, we generate RTL, we generate the verification environment, we generate tests for the RTL. So all is based on this single description. So you can have just one engineer who working on the codel, which is the name of the language, and the rest is generated automatically for you. And using this approach, because you have just single description, there's obviously you have to verify that, it's clear, but the amount of time and resources is much less than in the standard manual approach. So for the design tool, we have a tool that's called Studio. It's actually a bunch of tools. It's not a single one. It's been introduced in 2014, silicon proven by major vendors, and customers use it together with RISC-V IP a lot. So I already mentioned the codel, the description language that we use. That's like an input for the tools. And then the language itself is not really tied to any architecture or type of instructions. You can describe a really simple one. You can describe more complex one. You can even go beyond SIMD. You can have really crazy stuff there. If you want, if you are looking into really crazy stuff, you can do that. And then we have a bunch of generators. So I mentioned the RTL or VM generation. In the case of RTL, we have a backend for Verilog, System Verilog, and VHDL. In the case of SDK, we have LLVM-based compiler or Toolchain. In the case of verification, we generate UVM-based test bench or verification environment, including tests. You can use System C simulators that are also generated in, by Studio in your System C environment. So you can then have a virtual prototype using the ISS that is generated out of the Studio. Having said that, so I'm talking about the LLVM all the time, but you know, as you saw in the previous presentation, GCC works with our solution as well. So if you are in the standard configuration, which is okay for some customers, then you can use GCC as it is right now without any issue. But if you are looking for ISA extensions, then the LLVM is the one that should be used. So if you look into LLVM in more details, what that is, so I have just some kind of high-level overview of the LLVM and compiler and other tools that are inside of LLVM. So let's just dive into that. So LLVM is basically collection of several modules or libraries or tools, and some part of that is dedicated to compiler, and some other part is dedicated to linker or debugger. LLVM itself supports a wide range of architectures, so it's not just about RISC-V. You can have ARM backend there, you can have a x86 backend there, so it's quite robust. And thanks to the way how it's designed, it's reasonably simple to modify or extend. So we can, you can extend that with new instructions. You can extend that with new architectures, usually easier than the old or the big GCC framework. LLVM itself, it's a three-stage design. It means that we have a front end, then optimizer or middle end, if you will, and then finally the back end. So in the case of a LLVM, it's Clang as the front end, and Opt as the optimizer or mid end, and LLC as the back end. Right now, in the current version of Studio, we support LLVM 7.0.1. We are working on the 8th release, so it should be released quite soon in the next generation of Studio. So if you look at the three-stage design, what that actually means to ones that don't know. So at the beginning, as input, we have a C or C++ code that's parsed by front end, by Clang. And Clang then produces LLVM intermediate representation, IR for short. We have enhanced the front end with some new features, such as dual stack feature. So if you have some kind of SIMD architecture with scratchpad memories and you need to have dual stack, then this is implemented in our front end already. Then in the case of optimizer, well, it does the most target-independent optimizations. And again, we have added our own optimization passes that make code smaller or better performance, this kind of thing. So this is part of again. And most importantly, there is a backend, the LLC, and the backend itself is actually generated by Studio. So it's open. You can see the output. You can change the output if you want. You can add your things into backend if you want. And not only that, you can add your passes into front end or optimizer as well, because we have certain hooks that you can use to add your optimizations to your architecture if you have something already implemented in the LLVM domain. And the opt works with LLVM IR as well, and the output of the backend is, in the end of the day, the assembly code that goes to a linker, as you've seen as you saw in the previous presentation. So what we need to generate a compiler. So first of all, we need information about the registers for register allocation. So we need to know how many registers you have, which register files you have, whether you have dedicated registers or flags or whatever. So this is needed as the first step. Then the second step is that we also need the list of instructions, including patterns, to be able to schedule or select proper instructions. Basically, it's DAG, as you can see an example for ADD. So it's quite simple here, but if you can imagine more complex instructions, can be quite complex graph. And then we need also scheduling information, so things like memory latencies, delay slots if the architecture has one. This kind of information that you need to have a very good code. And last but not least is also ABI definition. In the case of RISC-V, it's more or less fixed, but if you need something else for whatever reason, then we can change it easily as well. So how we gather this information? So once again, everything is captured in Codel, in single description. So Codel itself is a C-like language. Again, it's not tied to any architecture or any kind of instructions. And in fact, even the BK series, the family that we have, is described using Codel. So we actually, we use Codel as well. So not only customers, but we internally use Codel as well. And on the right side, you can see an example of the definition of a register file. So you can see a 32-bit wide 32 register file. Then you can see the ABI definition that says, okay, stack pointer is one of the registers in the register file. And last but not least is the instruction definition that uses 3 register operands. Then there is assembly section that defines how the instruction looks like in the assembly, and binary that defines the opcodes and the things for the binary parser. And more importantly, there's a semantics section that defines the behavior of instruction. And here is quite simple. It's just do a multiplication and then store the result. You can have a really any kind of C code that makes sense, obviously, in semantics. So in this case, it's just one line. But you can have definitely more complex behaviors, such as, in this case, it's actually multiplication is MAC on a register file. But you can have a MAC that actually does more things, such as loading operands from the memory, storing the result, and at the same time, the pointers to memory are incremented. So everything can be then put into single instruction. So the MAC can be quite easy like this in this case, but it can be more complex, as I said, with loads and post-increment features. And then if we get this information, then the generation itself is then split into 2 phases, semantics and register extractor, and then the backend generator itself. So the purpose of a semantics and register extractor is to actually get a list of instructions with semantics to get patterns that the backend needs with a precise definition of the registers that it's going to use and so on. And then the compiler generation itself, it just uses the semantics, it uses the register info, it uses ABI and scheduling information to produce the final backend that's compiled as LLC in the end of the day. As you can see, the ABI scheduling information goes directly to backend generation because there is no need to parse it or do anything with that. It's just the definition. But in the case of semantic instruction, it's quite a complex task to find out every single instruction, including semantics and patterns. If you look at example, here is a real life example of MAC that we just did before a workshop. So it's MAC that works on the register file again, but this time the binary is RISC-V way. The rest is kind of the same as we saw in the previous slide. So 3 register operands. Then the assembly is quite simple. It's MAC, destination, comma, source 1, comma, source 2. The binary, then we split the opcode into 3 parts, and then the operands. And again, if you look at the semantics, it's quite simple here as well because we are working on the register file, so doing just multiplication, then the addition to the destination register in the register file. So this is how it's written in Codel, and now it's going to be parsed by the semantics extractor, and it produces a more friendly description to LLVM itself. So if you can see here, right now we know that we have operands that are registers. We have assembly and binary as well for the backend. And here you can see that the semantics has changed. It's LLVM IR actually. So you can see that we have 3 register operands, 32-bit wide, reg 0 up to reg 2. And then there is a multiplication and addition. And if you look at the multiplication, it uses 2 register operands, produces the intermediate results that goes to the addition that uses the intermediate results, and then another register operand. And then after that, the result goes to the destination register. So the point is that right now it's much more friendly to LLVM compiler and for the backend generator. And by the way, we also are able to generate the patterns. So here you can see on the right side, you can see the graphical view of the graph or DAG that's produced by the semantic extractor. But it's not the last step. The last step is then the final step is then the output for the backend, which is here, which is for anybody who's familiar with LLVM, it's a definition of IMAC, and the important thing here is again the pattern. So if you look at the pattern, it's textual form of the graph. So we have again the multiplication here and addition here that goes to the register file. You can see the constraint in this case. Then the output operand should be the same as the one of the register operand. Size is 4 bytes, 32-bit instruction wide. And then there is no load and no store. So this is the final step, and after that we have if we have collected like a list of these instructions, then the backend is happy because it knows every single instruction that it's inside of the ISA. So that concludes the LLVM stuff. So the key things to remember, I guess, here is that thanks to our solution, no matter how complex the instruction is, we are able to parse it and generate it to the LLVM. Obviously, if you came up with really crazy stuff, then the LLVM is not able to use the instruction automatically, and you have to dive into intrinsics. But if you have reasonably complex instructions, such as these ones, it's quite, you don't have to change the code, actually, in C code, I mean. You can just add instructions and compile it, and do the profiling, and see the results. Which brings me to different tools that we have inside of SDK, and one of them is a profiler. So profiler is really important. Again, we saw a presentation earlier about prof on the Linux side, but if you're assuming that you have a bare metal application, you need a profiler as well for bare metal stuff. So profiling in itself is just a dynamic form that helps you to find the hotspots or places that you should optimize. And in our case, the profiling can be used for either application optimization, or actually, you can use it for instruction set addition if you need that and if you're looking for that thing. So we support 2 modes right now. The first one is like tracking or watching, which means that you don't have to annotate the code at all. It's part of ISS that we have. And by the end of the simulation, you can get the list of used instructions or combination of instructions. You can see the annotation of a code on a picture. We can also, we also support annotations in a sense like gprof or LLVM coverage reports. So those parts are supported as well. So then it depends on the user whether he's into more tracking things or whether he's okay with a gprof and these kind of things. So the point is that the profile is generated as well, and it's aware of new instructions as well. So by the end of profiling, you can see, okay, so this new instruction is worth it because it saves me some time, and that's something that I'm into. Or you can see that, okay, the gain is not that much, and if I look at the size of the instruction, it's quite big. So let's think of other solution. So everything is possible and easier thanks to the profiler that's aware of any instruction that's inside of RISC-V. And last but not least, tool here is a debugger. So obviously, debugger is part of SDK as well. Right now, we are using LLDB in the same version, so 7.0.1. LLDB is part of LLVM project. So it's a C++-based debugger. It's again designed in a way that it's okay to extend that. It's okay to add a new target. It's okay to add certain features. So for us, it was obvious choice to use LLDB because LLDB is then aware of every single instruction that is inside of RISC-V IP. It uses LLVM infrastructure as well, so Clank is used there for any expression that you would like to evaluate in the LLDB. The disassembler that's part of LLDB is again, it shows nicely the new instructions whenever you're debugging either on the ISS or on the on-chip, because the flow is that LLDB, or in our solution we have an Eclipse-based IDE that talks to LLDB, and LLDB then can talk to either ISS or OpenOCD that talks to on-chip debugger. So from the user point of view, the nice thing is that you stay in the Eclipse-based IDE, And it doesn't matter whether you're using ISS or real chip, because the look and feel is the same. The environment is unified, which is quite useful for final software developers. Well, we sent abstract for the next workshop, so hopefully it's going to be accepted. And because I really want to share more details about LLDB, because it's a really nice software. And I like to share more info about how we enhance that in a way that it's full-featured now in our solution. So the key things to remember, I guess, would be like, Codasip is a pure-play IP RISC-V IP provider. So if you're looking to off-the-shelf configurations, if you're looking to RV32 IMC or RV64, whatever, we have it. You can use it, but we allow you to go beyond if you need. So if you need key differentiation, if you need some secret sauce, either in a form of ISS extension or in a form of microarchitecture tweaks, then you can do it. You can do it in-house, because the tools that comes with the IP, you can install it in your machines, and you can use it quite easily. And because we are using Codel as well, we are using our tools as well internally. We know that the tools are best in the class. The key differentiation is really a hot topic right now. And as we saw previously, the hardware-software co-design is something that we need. And thanks to the studio, it's easier for you to do that. Yeah, well, and by the end of the day, you have SDK and RTL that's aware of whatever you did. That's really helpful, and it's really high-quality product in the end. So I encourage you to look at our solution. Thank you.
I'll ask one. So you mentioned you've been doing a lot of work in LLVM and upstreaming it. Is there something that you would ask? Because it seems to me that GCC's had a lot of work and focus, and LLVM to a lesser extent. So my question to you is there certain work or something specific to further the development of LLVM that you'd ask?
You mean well, yeah. For instance, if you look at the vector extension right now, this is a nice example, because right now there is zero support, and this is something that we need to work together on, because it's a huge piece of work, and this needs to be done anyway, because we got, V extension is quite popular now, especially when 0.7 was released, and so this is joint effort. It cannot be done by a single person.
Are you going to release the SDK generation as a separate product for maybe other CPU vendors, or you are only providing this toolchain generation for your RISC-V products?
So the question is about whether we...
I mean, for example, if you take another RISC-V IP vendor, and are you providing this software generation as a separate product?
Well, it depends on the customer. Again, some of them are really happy with off-the-shelf, which means that they get IPs and from, I guess, you or other guys, just binaries and RTL that you can use. And if there is enough interest, then the tools comes with that. So it means that okay, just have a tool, and here's the model, change it, play with it.
Okay, thank you.